something, I guess, oxidative addition in terms of the orientations, all et cetera, to facilitate that.
Let's conclude with thanking Noel one more time. The morning session is concluded, but I think Dave has some things to say about lunch.
One thing, I want to acknowledge our sponsors for this, and they're listed in the front cover of the program. One addition is Altamira, which didn't make the program, but they have some literature next door. And Micromeridics has a display next door. Feel free to stop by and look at them during the breaks and introduce yourselves to the representatives. Lunch will be around the corner in the restaurant. Again, if there's problems, it's something you can't eat at the buffet, let us know. We can make special arrangements for you. There's a box out on the registration table for your badges. Before you leave the meeting, please return your badge covers and badge if you want. We can recycle them again next year. Ballots are also out there on the registration table. If you're a Tri-State Catalyst Society member, please vote and turn them in. We will announce the winners at the reception tonight. That'll be all for now.
Union Carbide. I guess we can still say Union Carbide.
It still is.
It still is.
100%.
Many, many years there. Dr. Bhasin is a corporate fellow at Union Carbide, and he oversees the heterogeneous catalysis. He has done a lot of work in ethylene oxide catalysis, and now is in charge of the long-range hydrocarbon programs. He has many, many interests has been involved in many fields of catalysis, including surface science. I know he's taught me a lot about statistical design. He's done both applied and fundamental work. And he's been very, very well known in his career. In 1993, he was awarded the Hoodry Award by the North American Catalysis Society, which is quite an honor. And last year in 1999, he was ACS Industrial Chemistry Award. So we are very pleased to have him with us today, and he is going to, his talk is entitled Novel Catalyst System for Treating Exhaust Gases from Internal Combustion and Stationary Source Engines. His co-author is Dick Nagaki. Okay, turn it over to Dr. Bhasin. Let's see. You have everything you
Somebody
need?
said I should try this, but I don't think I need one. Otherwise, I'll come out too loud. Is that? Can you all hear me at the back? Yeah. It's indeed a pleasure to be here at the Spring Symposium. Looks like, Pat, you had also gotten me into another one of these a year or so ago, so you're becoming a regular speaker here.
Well, you do such a good job.
Oh, thank you. You're kind. Hope I can do as well. And then Bob Ferentz has told me that I better set a good example, so let's see how we do. What I'm going to share with you is a very interesting, exciting development that was truly out-of-the-box thinking, and indeed represented a paradigm shift. Before I go into any of that, I want to ask a general question. How many of you have been involved with or have worked in the area of automotive emission control? 1, 2, 3, 4. Okay. And currently still involved? Oh, yeah. That's great. So Wolfgang can give me a hard time. And what I'm going to then do is give you a little bit more introduction, and that's the reason I was taking that quick survey, is to see how much of introduction I need to give for this talk. We do have plenty of time, so we'll go at a more relaxed pace. As you all know, 1990, U.S. Congress passed the Clean Air Act, and as a consequence, the automakers screaming came along to accept the idea that they should meet the low emission and ultra low emission standards, which of course California was leading the way. I think you all are pretty much aware of the challenging problem they have in Los Angeles and in other areas in California. So that was pretty much the driver behind going to the low emission of automotive exhaust. Incidentally, before I go into that, there's a very interesting story that tells you about how much emissions do come if you don't have a catalytic converter. A few years ago, Razi probably remembers, we had a building evacuation in our technical center, and we soon found out the evacuation was a result of a carbon monoxide alarm. As you know, we do a lot of low pressure oxo research, so we deal with carbon monoxide all the time, and we have never had any incidents. So when they checked all the oxo laboratories and all, they couldn't find any carbon monoxide, but they were reading it. It was real. And at the end of all that, when they really tried to find out what's going on, guess what was going on? At close to the air intake for the building, there was a forklift truck which do not have any kind of control device, emission control device, and it was putting out carbon monoxide at a percent level, a small engine at percent level. In the building, it was reaching several ppm in carbon monoxide. So that tells you one thing, that be aware of those that do not have any auto emission control device. And second thing, as a general warning and help to you all, the kind of engines they use are even less sophisticated on your lawnmowers. So always be extra careful not to come anywhere close to the exhaust of, the lawnmowers, okay? So that's the kind of things we were talking about. So as a consequence, the challenge was in the 80s and 90s was to reduce these emissions, not from a few hundred ppm level that are coming out of the uncontrolled vehicle or from a old technology, but to go down to a few ppm. So it's a 99, 95, 99% reduction. And as you know, most of the catalysts in the 70s have gone to what you call the three-way auto emission control, that is oxidizing CO and hydrocarbons to convert to carbon dioxide and water. And we're not going to worry about the greenhouse effect here because automobiles do put out a lot. But to make sure then the nitrogen oxides are reduced to nitrogen. Now, can you imagine a catalytic challenge? I don't think there is any other, and that is under oxidizing condition, you convert CO and hydrocarbons to carbon dioxide, and NOx, all the three kinds in there, mainly NO and NO2, to convert to the nitrogen, to harmless nitrogen, and do that all in 90-some% selectivity or better. So all these years, as a hard work of thousands of researchers in various automakers, academic, and others, they had developed a three-way catalyst system, which is typically had noble metals, palladium, platinum, rhodium. Rhodium typically doing the NOx reduction, and palladium, platinum doing the CO hydrocarbons oxidation, and then combined it with some unsteady state catalysis. I'm going to take another poll. How many of you know that the unsteady state catalysis has been used for a long time now and commercially practiced underneath your car? And that is, in order to achieve this kind of reduction, you're alternately cycling the concentration of oxygen, which is higher during the oxidation phase to get rid of CO hydrocarbon, and during NOx reduction it is low to make sure you reduce NOx to nitrogen with the help of hydrocarbons and CO. Anyway, all of these catalysts developed to date have been assuming that the only way to get high catalytic activity, as you all know, is by putting a wash coat of an amorphous phase, gamma alumina typically, or transition alumina, combined with some additives, and put that onto very low surface area cordyroid. Cordyroid typically has only about 1 square meter per gram. They put that onto that wash coat, and then now they're trying to put the palladium platinum on it and rhodium either combined together in the same wash coat or separately to keep some of the metal and metal oxide separate so as to get the optimum performance. So it was always puzzling to me. I remember my dear friend from Ford Motor Company and GM, that's Harun Gandhi and Kathleen Taylor, asking them that, gee, why can't you do it all on a simple support like alpha alumina? Well, the first answer was the surface area is too low, it's 1 square meter, and we have 1 square meter cordyroid, and if we put anything on that cordyroid, it does not work worth a darn. You know, it's a pretty lousy catalyst. Well, that we knew that, we confirmed that. But the challenge still remains. So got back into the lab and did some probing experiments, and we saw some very encouraging things early on, and that's what led to proposing this project in Union Carbide. We are not in automotive catalyst business, and developed a technology that I want to share with you today and show you how we were able to not only achieve a paradigm shift through this out-of-the-box thinking, so it's a good experiment in learning in that, but also the performance was better than what they had, automakers had in development, not currently commercialized, what they had in development coming up in the pipe. Where we are with it today, we have this technology. It's been scaled up and available, but we did not see as good a strategic fit for Union Carbide to go all the way into the automotive catalyst business. So that's where we are, but we'll show you through these tests. So that's the story I want to share with you. Real exciting, and as I say, representing a paradigm shift in emission control catalysis. Why a paradigm shift? Our previous prejudices have been that you need very high surface area. Wrong. You don't need it. Alpha alumina, which is very much like the cordyroid base, has very low surface area. And the low surface area is there, but if you can make the catalyst properly, and we'll talk about that once you have it, it's on a really stable support. Okay, so the prejudices have been that the activity is low, you cannot get enough metal dispersion, and this is where some of our work in the 60s and 70s came to help. We had worked with alpha alumina in supporting and making high dispersion of palladium platinum, and that's where that came handy. Then they say the aging is poor, and because it's already low surface area, particle size is higher, you're going to agglomerate and all that. And very difficult to make desirable compositions, meaning being able to put the oxidation catalyst and the NOx reduction component together in a manner not to cause alloy formation, not to cause other interaction with the support. You can list a whole bunch of these, and I will not go into that, but the developments that were made, and commend those developments because I think they made the challenge even harder by taking a wash coat which is not compatible with the cordyroid. Cordyroid has exceptional thermal expansion coefficient, very low. So it's way down there. But then they're mixing it with alumina, which has high factor of 10 higher thermal expansion coefficient. And then they got into the challenges of wash coat adhesion, how well it adheres together. They have a test in automakers that's called wash coat adhesion test, meaning as you cycle through temperature, can you keep it together? And basically, it's a very impressive story. On the other hand, I think they put themselves in a box unnecessarily than they had to. Am I going about the right pace? And keeping you all awake? That's the other challenge after lunch. I have the easy job. I have to stand up here. So what is NewCat that Union Carbide developed and collectively in working with the ceramic makers, Norton Chemical Process and Products division of Saint Gobain. We worked with them to develop this alpha aluminum monolith. It is definitely non-wash coated, and I cannot tell you this enough. Every time I went to our potential customers, all of them, they would always ask, "You mean there is no wash coat?" I said, "Yes." I had to be nice to all of our potential customers. Even though they asked second, third time, I said, "Yes, no wash coat." But then how does this metal stay together and does not fall off? Well, I said, well, we've been using silver catalyst on alpha alumina all these years. It's also particulate, and it hangs together for years and years. We haven't had any problem. I can't tell you the theory of that adhesion, but it does stay together. So we put these catalysts through the paces, through adhesion test, through a whole bunch of other tests. And since these tests are different, when I get to those, I'll make sure go over a little bit more slowly because they're not the usual tests we do. So that's the story, and the reason we chose alpha alumina is we've been able to, working with Norton, develop supports that are not only very high purity in alpha alumina and very few impurities, but we know the role of those impurities. We know what they do, and we can not only control them, but put things that are to the advantage. Well, why use it? Well, it has high temperature stability. When you're putting corduroy on it, the gamma alumina, guess where it's going to go? When you have high temperature cycling, it's going to go downhill to thermodynamically stable alpha alumina. And when it's trying to go downhill, the activity decline is almost exponential, and the reason is that the whole metal is getting trapped. As the structure of the alumina, porous gamma alumina collapses, it goes and traps the noble metal. So we were looking for that high temperature stability, and the reason for looking at high temperature stability was that you want to be able to put the catalyst very close to the engine, and you could put close to the engine, the temperature rather than being 1,000 degrees now will be 1,400 degree max temperatures. And we were able to get very good NOx reduction activity. In fact, when we started out, I had no, no qualms about being able to convert CO and hydrocarbons to CO2, but to get the NOx reduction activity, that was my biggest worry card, but we were able to do that through some very nice combination of metal dispersion, metal oxides, and their combination made in a special way, and that's the rare earth metal oxides, typically using lanthanum and cerium oxides. So the advantage of this technology is it can give you something, a catalyst that is very high temperature stable, hence you can keep it close to the engine. Now what are the advantages of keeping it close to the engine? You know, unlike our catalytic reactors, there is no place to heat the catalyst up, right? The only way you heat it up is to burn some carbon monoxide and hydrocarbons, and that provides you the fuel to heat up the catalyst. Well, if you keep the catalyst about 8 feet away from the main engine through this convoluted exhaust pipe, then it's going to take you quite a few minutes. And in fact, the typical emissions, more than half of the federal test procedure, FTP cycle, occur in the first couple of minutes, you've done enough damage. So then the advantage is that by keeping it close, you're able to heat up the catalyst mass very quickly and start the oxidation process going and providing you energy, which then can be used with another catalyst like we have currently underneath the car. So this catalyst system is what we developed in, and we have composition of matter on both the support as well as Union Carbide patenting the catalyst compositions, which are namely noble transition metals and noble metal combinations incorporated onto alpha alumina. Get comfortable. I'm going to ask everybody, please stand up. No, really. Take a stretch. No need to. This way, that way. And take your coat off because I think. Yeah, I saw you there, Bill. You didn't fall off yet. So okay. Our historian is ready? Yes. Okay, so what is the new CAD composition? As I said, it's really very simple, and that simplicity, as you will see, has a lot of other advantages as well that I'll share with you in a minute. Once again, no wash coat. We put the noble metal impregnated onto the porous alpha alumina, and it just goes as a varying particle size of noble metal, and combine that with promoters, either in 1 or 2 impregnations, and we're done. You dry calcine, and the catalyst is made. So that's the current, that's our catalyst. The way they've been trying to do, in, as I say, very novel, challenging way that they've done it over the years is, if this is your backbone corduroy support, you put the wash coat here, and then in the wash coat you put the noble metal, which has smaller pores. And this, by the way, is the other disadvantage, is that one of the difference why we were able to do it on very low surface area, much lower metal dispersion is that our effectiveness factor is much higher, because we're talking about micron size pores and they're talking about 100 angstrom pores. And that is another big factor. And then making sure once you have made it, that it remains stable. Stability is the key, okay? I kind of touched on some of these, but let's go systematically. Why use alpha alumina without a wash coat? The base, in case of the current technology, is a corduroy, very good, but its only melting point is only 1450. You say, oh, gee, that's pretty high. Well, it's not high enough, because when you get excursions and in the engine, and if you're going to put it close to the engine, that temperature can be easily exceeded. In fact, we did some tests at Southwest Institute to simulate an engine misfire. You know how occasionally it happens. And we showed where the current catalyst is totally melted, and alpha alumina based our technology came smiling through. And the difference is about 600 degrees in temperature. Melting point of alpha alumina is very high. And by the way, this of course is dependent on the, again, purity, and why we emphasize fairly high purity alpha alumina. Otherwise, this will not be as quite as good. Then they add high surface area alumina wash coat for porosity and metal deposition, and we don't need any. And we do some neat tricks whereby the rare earth oxides and the like, they provide you with extra nice catalyst structure within the pores of alpha alumina. This inherently unstable, and as you heat it up, it's going to go toward theta and then toward alpha alumina, and we are starting with the most stable phase, and and hence that is a big advantage. Typically, in the current technology, they would be using multiple steps, or if they want to keep rhodium away from palladium platinum, they will have one little part of wash-coated metal made with one metal, and then another one with another. Then you put it together, then you make the whole wash coat. So you can see it's really quite challenging. They do it though, commercially. Simpler catalyst preparation. And this last one, cannot overemphasize at all, is that typically because of the low metal loading you have in these typical catalysts, the noble metal recovery is only 90%. You're talking about expensive metal, palladium, platinum, and rhodium. And we're talking near 100% because there is no place for alpha alumina to go or to trap anything. So with a simple extraction process, we were able to typically get 99+% recovery. And that's a big advantage, especially when you're talking about very large volume of inventory of these expensive metals. The catalyst that we're going to be talking about is there are three compositions that I'm going to just share with you as examples. By the way, this column somehow, this row somehow moved. This is palladium, that's platinum, that's rhodium, and this is surface area, and not there. So, something happened there. And so the palladium, platinum, we initially started with high loading, thinking we need a lot more. We found out we do not need that much. So the next compositions were quite a bit lower, and then we settled to somewhere in between metal loading of palladium and platinum. And this composition also has rare earth oxide. The first two does not. And you'll see the rare earth oxides do provide the extra conversion of NOx to nitrogen, and that's due to a palladium-platinum interaction with the rare earth oxide. So just remember, number 3 has rare earth oxide, number 1 and 2 are simple palladium-platinum catalysts. The surface area is all typically less than 1, and for the commercial catalyst, it's one was Honda Accord, of course, wash-coated cordierite, and an S-cord. Now, the metals in S-cord does not have any palladium, but has platinum, rhodium. Surface areas after their 200 square meter wash coat of 10 to 15% would be expected to be in this range. And this Accord also has palladium, platinum, and rhodium, all 3 components, to achieve the 3-way conversion performance. And in terms of volume, we kept it very close to make sure that we're comparing on the same basis, because there's no point in having activity if I'm going to wind up requiring a bigger can underneath the car. It doesn't do any good. So they're all about 1.3 liter in volume. And the cell density, this has to do with how effectively the gas is flowing. We started with low cell density, 100, but soon matched very close to what's commercially being used, 300 cell. It's in both units of per square centimeter and per square inch. And wall thickness, again, was high initially. That's a consequence of having low cell density. And then we reached a wall thickness also very close to what's commercially being used. Important part of this is that this has to do with how well your frontal area is and how well your catalysts are going to do in terms of pressure drop, which is very, very important. In terms of packing density, again, these units are mixed up, but this is grams per milliliter. It's typically all same, and when you go to 400 cell per square inch, then your density is lower because you don't have as much mass. So key thing to remember, number 1 and 2 catalysts are without any rare earth, lanthanum, cerium. This contains lanthanum cerium, and this is the one I'll be spending more time, but I'll show you where this catalyst system performs and how it compares with Honda and the Honda and the Escort. Okay, now very unusual aging cycles, and this is to simulate thermal shock. And what you do is have the engine, since that's the one providing you with the temperature, as I said, to the catalyst. If you have idling low RPM running engine at 800, your temperature would be low. This is the bed temperature in the catalyst. The inlet gas is at 320. And you're cycling between 320 and 900 to see how well your catalyst will stand. Now, that's pretty good shock, isn't it? And we'll show you, we're doing it in minutes, cycling back and forth through this trick. And so basically you increase the load on the engine and accelerate, and you get the higher temperature. Okay, so you're putting more hydrocarbons and carbon monoxide, more fuel to it. And this is shown graphically here, and that is time versus time. You ramp up very quickly in about a minute, minute and a half, from 300 some to close to 900, and then you hold it there for a little while, a couple of minutes, come down, ramp it up again, and this goes on in minutes. So we do this cycling for quite some time. Now, most of us have gone through accelerated aging tests. I don't think any of you have done this accelerated aging test. How high a temperature you think you would normally put your catalyst in? Few hundred, 800, 900? Well, we went up to 1400 centigrade. And this is called, we call it the
carbon fibers in 2000.
2000. This one, Southwest Research Institute, who did the test for us, we did not have this facility, so we went to the best in the business. That's Southwest Research Institute, independent institute, does the testing, and they called it high temperature destruct test. So deliberately, they run it at very high RPM anyway, but then they pull one of the cylinder, and this is something to behold. I mean, you're talking about your muffler, everything, the exhaust gas, so high it's glowing, okay, glowing red. You can tell the temperature from just looking at it. And then but at a fairly high load, the load goes down a little bit because you're taking one cylinder out to simulate misfire, and the inlet temperature goes off, it goes down very low. But anyway, because you have a lot more air and hydrocarbon fuel going through, the temperature now reaches 1400. And look at the catalyst bed temperatures, stable meaning running at 1200. So this one is what typically corduroy type catalyst system can survive. That is 1200 degrees centigrade in the bed, and they typically run this for half an hour to an hour. But for a short time, you run this high temperature destruct, the real killer test, right? Now, the results of the killer test first. The one on the left, on the top, I beg your pardon, is the inlet face of the Honda Accord. Big hole in the inlet face as the exhaust went through. They had a two brick configuration, same volume, but it's two different bricks. Probably again splitting the kind of palladium, platinum, rhodium they're doing. And this one is got smaller holes. And this the same test with our alpha alumina based catalyst, and there's no change at all. The picture is not as good the second time. Now, what does the catalyst do under these conditions? Is I should speed it up. I was going too easy. Okay. Let's see. Fine. Okay. The test here is what they call efficiency is actually conversion, but that's the terminology. Oops. Oops, maybe. It is conversion, and the conversion for our union carbide catalyst composition 2 before and after. That means after some high temperature aging cycles, and then testing back at 500. And this is the Honda Accord through the same aging cycle. It drops, it starts higher, but remember this is the one that did not have rare earth oxide in it, so it's not quite as good a catalyst to begin with, but then our catalyst did not drop hardly very much at all. So this is before and after, and this is the before and after reduction in conversion for carbon monoxide. For the other test this is for hydrocarbon now, is the Honda Accord is here initially, and they drop down to a significant level. Say here it'll be 80 to 40 at this level. Everybody familiar with this thing here? That's the air to fuel ratio, and this is the stoichiometric regime, and this is where your your engine will be going through air-rich side and fuel-rich side. So that's the stoichiometric point, but that's where they're cycling. Typically your catalyst is cycling between air to fuel ratio somewhere between here. But as a standard test, they go to even lower level and a higher level to check how it's doing. Again, much less reduction in activity. So basic stability, we're showing we're already better than, even without having rare earth oxides, which by the way commercial catalysts do have, but our first versions did not. Now this was a total surprise. We did not have the rare earth palladium metal combination that's needed to do NOx reduction. But there are some of those metal oxides present in the alpha alumina. And there's some strange interaction going on, because instead of look at the Honda Accord for NOx reduction to nitrogen, it goes from here to almost nothing. And this is very likely because they have rhodium containing catalyst, and rhodium containing catalyst will undergo on a accelerated aging test at high temperature. It will significantly reduce in NOx conversion. But for our composition, which was not very good to begin with, but it became better with aging. And this says, again, we have some explanation for it, but I'll spare the time and go to the more exciting catalyst number 3, which is comparable in composition to what is commercially being used, but it is on alpha alumina and no wash coat, okay? And that is this hydrocarbon conversion test. The standard error in this test is about 5% or so. So all of these 3 tests are same, even though it looks like Accord might be a little bit inferior under high region. But in this region, they're all within the noise level of the measurement. And our carbide composition looks like it was somewhere in the middle, but I'd say they're all about the same. Now, that's for the hydrocarbon. Now look at the I think I'm going to skip this one, just go to the carbon monoxide. There is some initial activation of our catalyst that we saw, but the more important thing is what is it doing after we have fully activated. And that is, now look at this one. Remember I was telling you the catalyst for the next generation of low emission got to achieve 95 to 99% conversion. These are again now getting within the noise level. This is essentially complete conversion here at the stoichiometric point where they will be operating. So that's for all three catalysts operating very similarly. Same thing now, and since we have now formulated to take care of the NOx reduction catalyst composition with the proper mixing of the noble metal and the rare earth oxide, and this in green is the carbide composition. Again, this is all noise in the numbers. This is the place they will be operating. Now again, the NOx conversion, the way they do it, is not coming out very high. It's because of the function of this test. It has very little to do with the actual performance. Will be again in here, in that region. But hydrocarbon that just shows up essentially complete, because once you reach with a good catalyst the right temperature and your catalyst is in a stable form, it's essentially same. Another important parameter is how quickly the catalysts light up, right? Because if you don't light up or you have too much mass, it's not going to work. We showed that our light up time again for hydrocarbon and CO essentially same as the Ford Escort version, even though ours was not at that time fully activated. Well, we tried to look into these catalysts as to what was really going on, and we did a number of tests to try to find out as to the stability that we were seeing, and we wanted to make sure we do that under controlled conditions. So in the controlled conditions, what we did was have a synthetic mixture of 500 parts per million of typical hydrocarbons that you see, which is, in this case, we simulated with ethylene, ethane, and methane, okay? And also to determine what kind of activity, olefin versus paraffin, and ethane versus methane we're seeing. And we were just pleasantly surprised how well these catalysts do, and then how well they're able to retain that activity. Mind you, that is the key. How well can you maintain it over a long period of time? So for this simulation, laboratory simulation, we steam treated the catalyst, not at those high temperatures, more for automotive tests, but typical standard tests, and took the composition number 3, which is palladium, platinum, and rare earth oxides, and accelerated aging versus a typical. In this case, we did go to Chevrolet catalyst, but we could have picked any. They're all essentially same, okay? They all have different ratios of palladium, platinum, and rhodium, but they're all essentially same. So this is to see under controlled conditions how well do we do. So for methane combustion, this is the Chevy catalyst, and our carbide catalyst, the filled circle for methane. Pretty good initially, the Chevy catalyst. It just continues to age, while our carbide composition, this again some noise in the data, but at longer time it's essentially remains unchanged. Okay. Everybody familiar with T50? That's the temperature for 50% conversion. It's indicative of inversely indicative of activity. So higher the temperature, lower the activity. For ethane, on the other hand, also we saw, well, of course, lights off earlier at lower temperature, 600 degrees. But again, other than this point, all of these essentially again showing no loss in activity for this 900 degree steam test. And this is consistent with the higher temperature test that I was showing you earlier, where we saw, again, very small drop in activity. Ethylene, on the other hand, again, Chevy catalyst is all fully formed, and we know ours was activating, and that's the couple of graphs I didn't show you, was that our catalyst composition, to get the right interaction of palladium, platinum, and rare earth oxide, we had to do some, either run it in the reactor or we can run it outside And we've done that study as well. If we can calcine it at a certain temperature to promote that interaction, that you will get that same interaction and improved performance. So in this case, we start not as good, but then very quickly as it activates. But again, there is no change in performance over the life of this test. And again, Chevy catalyst with the wash coat and all that, and rhodium in it. Very important thing to remember. We were able to get the NOx reduction to the right level, carbon monoxide, hydrocarbon conversion at the right level. We never felt like we needed rhodium. And very interesting, this work is 5-6 years old, and we were developing our version of rhodium-free catalyst. Eventually went to palladium-only catalyst. Wolfgang, you remember that development right in the Detroit area, very exciting. And that's when the price of palladium began to go up, and now it's even more than platinum. We had independently come up with a rhodium-free composition that does the conversion, but also you saw it does the NOx conversion just as well. So anyway, this kind of was a laboratory way of showing that we needed to form this palladium platinum with adjacent to the lanthanum cerium. Once that interaction is made and the catalyst is stabilized, then it's going very good for long periods of time. Incidentally, even though we start with 1 square meter alpha alumina, the surface area is much higher, because the lanthanum and cerium that we're putting in, primarily lanthanum, is enhancing the surface area, because forming an amorphous oxide-oxycarbonate phase, which has surface area. So again, lanthanum is very refractory. It does not change its character at all, so it gives you that very stable configuration. So I'm gonna wrap up and let you all ask questions. In summary, union carbide's NuCat technology that was with without the lanthanum cerium type of composition and higher cell density, but on that one we showed that non-rhodium containing, non-wash coated, that is without any, and lanthanum and cerium ages at significantly lower rate, even though its initial activity is somewhat lower, but it improves in activity on aging for NOx reduction, and that's coming from the noble metal rare earth oxide interaction, and it's superior to Honda on aging, and showed you also how this catalyst can withstand 1200 degree high temperature aging, as well as engine misfire conditions that can occur, and which will take the temperature to 1400 degree plus. And we're under same condition, the Honda Accord catalyst really melted. And then going to the more advanced compositions, which incorporate palladium platinum and rare earth lanthanum cerium type of compositions. They're again non-rhodium, non-wash coated, so we got rid of that. Finally, they all begin to believe us in the automotive world that indeed we can make this. But the initial performance was equivalent to Ford and Honda, and in terms of hydrothermal stability, they were definitely superior. My friends, that truly represents a paradigm shift. So I encourage you all, anytime you're looking at some technology, look at critically, but also step back and look at some other simpler solution to the same problem. And I'd like to conclude that this non-wash coated NuCat technology is on low surface area alpha alumina, has the initial performance equivalent and superior accelerated aging. Incidentally, I did not mention, but because it's not been approved for publication, but we have extensive testing done by automakers to show the same thing under their aging conditions, under their wash code adhesion tests and all that. Yeah, but it's and then these formulations on Alpha Luna have indeed a 600-degree operating temperature advantage, and hence can withstand much higher temperature, which one would see when you're close to the engine for reducing emissions even further. And that you can take advantage of that in a variety of ways to meet the future emissions regulations. Really, it was an exciting project. Dick Nagaki and I had great fun, and we have it available. And I'd like to thank you all for your attention and staying awake.